Hey, altruistic followers and ardent fans, I presume yourself your dear and near are in fine feather. It's analyst from Teacher Professor A. Suresh back with a clear expressive for my 86th video on unveil of publication on YouTube today, 30th September 2020. Topic for discussion today is artificial intelligence AI. What next? Intelligence has been defined in many ways: a capacity for logic, understanding, self-awareness, learning, emotional knowledge, reasoning, planning, creativity, critical thinking, and problem solving. More generally, it can be described as the ability to perceive or information and to retain it as knowledge to be applied towards adaptive behaviors within an environmental context. And intelligence is more often studied in humans but has also been observed in both non-human animals and in plants. Intelligence in machines is called artificial intelligence (AI), which is commonly implemented in computer systems using programs and sometimes specialized hardware. The word intelligence derives from the Latin nouns intelligentsia, intellectus, which in turn stem from the verb intelliger, to comprehend or perceive. In the Middle Ages, the word intellectus became the scholarly technical term for understanding and a translation for the Greek philosophical term nous. This term, however, was strongly linked to the metaphysical and cosmological theories of teleological scholasticism, including theories of the immortality of the soul and the concept of the active intellect, also known as active intelligence. This approach to the study of nature was strongly rejected by the early modern philosophers such as Francis Bacon, Thomas Hobbes, John Locke, and David Hume, all of whom preferred understanding in place of intellectus or intelligence in the English philosophical world. Intelligence has therefore become less common in English language philosophy, but it has later been taken up. Individuals differ from one another in the ability to understand complex ideas, to adapt effectively to the environment, to learn from experience, to engage in various forms of reasoning, to overcome obstacles by taking thought. Although these individual differences can be substantial, they are never entirely consistent. A given person's intellectual performance will vary on different occasions in different domains as judged by different criteria. Concepts of intelligence are attempts to clarify and organize this complex set of phenomena. Although considerable clarity has been achieved in some areas, no such conceptualization has yet answered all the important questions and commands universal assent. Instead, when 2 dozen prominent theories were recently asked to define intelligence, they gave 2 dozen somewhat different definitions. Human intelligence is the intellectual power of humans, which is marked by complex cognitive feats and high levels of motivation and self-awareness. Intelligence enables humans to remember descriptions of things and use those descriptions in future behavior. It's a cognitive process. It gives humans the cognitive abilities to learn from concepts, understand and reason, including capacities to recognize patterns, innovate, plan, solve problems, and employ language to communicate. Intelligence enables humans to experience and think. Evidence of a general factor, G factor, of intelligence has been observed in non-human animals. The general factor of intelligence, or G factor, is a psychometric construct that criticizes the correlations observed between an individual's scores on a wide range of cognitive abilities. First described in humans, the G factor has since been identified in a number of non-human species. Cognitive ability and intelligence cannot be measured using the same largely very verbally dependent scales developed for humans. Instead, intelligence is measured using a variety of interactive and observational tools focusing on innovation, habit reversal, social learning, and responses to novelty. Studies have shown that G is responsible for 47% of the individual variance in cognitive ability measures in primates, and between 55% and 60% for the variance in mice. These values are similar to the accepted variance in IQ, intelligence quotient explained by G in humans, 40 to 50%. It has been argued that plants should also be classified as intelligent based on their ability to sense and model external and internal environments and adjust their morphology, physiology, and phenotype according to ensure self-preservation and reproduction. Artificial intelligence (AI) is both the intelligence of machines and the branch of computer science which aims to create it. The study and design of intelligent agents or rational agents, where an intelligent agent is a system that perceives its environment and takes actions which maximize its chances of success. Kaplan and Heinlein defined AI as a system's ability to correctly interpret external data, to learn from such data, and to use those learning to achieve specific goals and tasks through flexible adaptation. Achievements in AI include constrained and well-defined problems such as games, crossword solving, and optical character recognition, and a few other general problems such as autonomous cars. Dental intelligence or strong AI has not yet been achieved and is a long-term goal of AI research. Among the traits that researchers hope machines will exhibit are reasoning, knowledge, planning, learning, communication, perception, and the ability to move and to manipulate objects. In the field of AI, there is no consensus on how closely the brain should be simulated. Artificial intelligence (AI), sometimes called machine intelligence, is intelligence demonstrated by machines unlike the natural intelligence displayed by humans and animals. Leading AI textbooks define the field as a study of intelligent agents, any device that perceives its environment and takes actions that maximize its chance of successfully achieving the goals. Colloquially, the term artificial intelligence is often used to describe machines or computers that mimic cognitive functions that humans associate with the human mind, such as learning and problem solving. As machines become increasingly capable, tasks considered to require intelligence are often removed from the definition of AI, a phenomenon called as the AI effect. A quip in Tesla's theorem says AI is whatever hasn't been done yet. For it, the instance, optical character recognition is frequently excluded from things considered to be AI, having become a routine technology. Modern machine capabilities generally classified as AI include successfully understanding human speech, competing at the highest level in strategic game systems such as chess and Go, autonomously operating cars, intelligent routing in content delivery networks, and military simulations. Artificial intelligence was founded as an academic discipline in 1955, and in the years since has experienced several waves of optimism, followed by disappointment and the loss of funding, known as the AI winter, followed by new approaches, success, and renewed funding. For most of its history, AI research has been divided into subfields that often fail to communicate with each other. These subfields are based on technical constraints such as particular goals, the use of particular tools, or deep philosophical differences. Subfields have also been based on social factors. The traditional problems or goals of AI research include reasoning, knowledge, representation, planning, learning, natural language processing, perception, and the ability to move and manipulate objects. General intelligence is among the field's long-term goals. Approaches include statistical methods, computational intelligence, and traditional symbolic AI. Many tools are used in AI, including versions of search and mathematical optimization, artificial neural networks, and methods based on statistics, probability, and economics. The AI field draws upon computer science, information engineering, mathematics, psychology, linguistics, philosophy, and many other fields. The field was founded on the assumption that human intelligence can be so precisely described that a machine can be made to simulate it. This raises philosophical arguments about the mind and the ethics of creating artificial beings endowed with human-like intelligence. These issues have been explored by myth, fiction, and philosophy since antiquity. Some people also consider AI to be a danger to humanity if it progresses unabated. Remember Terminator and I, Robot movies? Others believe that AI, unlike previous technological revolutions, will create a risk of mass unemployment. In the 21st century, AI techniques have experienced a resurgence following concurrent advances in computer power, large amounts of data, and theoretical understanding, and AI techniques have become an essential part of the technology industry, helping to solve many challenging problems in computer science, software engineering, and operations research. The study of mechanical or formal reasoning began with the philosophers and mathematicians in antiquity. The study of mathematical logic led directly to Alan Turing's theory of computation, which suggested that a machine by shuffling methods as simple as 0 and 1 binary could simulate any conceivable act of mathematical deduction. The insight called that digital computers can simulate any process of formal reasoning is known as a Church-Turing thesis. Along the concurrent discoveries in neurobiology, information theory, and cybernetics, this led researchers to consider the possibility of building an electronic brain. Turing proposed changing the question from whether a machine was intelligent to whether or not it is possible for machinery to show intelligent behavior. The first work that is now generally recognized as AI was McCulloch and Pitt's 1943 formal design for Turing's complete artificial neurons. This field of AI research was born at a workshop in Dartmouth College in 1956, where the term artificial intelligence was coined by John McCarthy to distinguish the field of cybernetics and escape the influence of the cybernetist Norbert Wiener. Attendees Alan Neville, Herbert Simon, John McCarthy, Marvin Minsky, and Arthur Samuel became the founders and leaders of AI research. They and the students produced programs that the press described as astonishing computers were learning checkers strategies in 1954 and 1959, were playing reportedly better than the average human, solving word problems in algebra, proving logical theorems, and speaking English. By the middle of 1960s, research in the US was heavily funded by the US Department of Defense, and laboratories had been established around the world. AI's founders were optimistic about the future. Herbert Simon predicted machines will be capable within 20 years of doing any work that a man can do. Marvin Minsky agreed, writing, within a generation, the problem of creating artificial intelligence will substantially be solved. They failed to recognize the difficulty of some of the remaining tasks. Progress slowed in 1975 in response to the criticism of Sir James Wright Hill and ongoing pressure from the US Congress to fund more productive projects. Both the US and British governments cut off exploratory, exploratory research in AI. The next few years would later be called as AI winter, a period when obtaining funding for AI projects was difficult. The early 1980s, AI research was revived by the commercial success of expert systems. Expert systems basically replicate the logic of a expert. Form of AI program that simulated the knowledge and analytical skills of human experts. By 1985, the market for AI had reached over $1 billion. At the same time, Japan's fifth generation computer project inspired the US and British governments to restore funding for academic research. However, beginning with the collapse of Lisp machine market in 1987, AI once again fell into disrepute, and a second, longer lasting hiatus began. The development of metal oxide semiconductor MOS, very large scale integration VLSI, in the form of complementary MOS, CMOS transistor technology, enabled the development of practical artificial neural network (ANN) technology in the 1980s. In the late 1990s, and the early 21st century, AI began to be used for logistics, data mining, mechanical diagnosis, and other areas. The success was due to increasing computational power, greater emphasis on solving specific problems, new ties between AI and other fields, and a commitment by researchers to mathematical methods and scientific standards. Deep Blue became the first computer chess playing system to beat a reigning world chess champion, Garry Kasparov, on 11th May 1997. In 2011, a Jeopardy quiz show exhibition match, IBM's question answering system Watson defeated the greatest Jeopardy champions Brad Rattler and Ken Jennings by a significant margin. Faster computers, algorithmic improvements, and access to large amounts of data enable advances in machine learning and perception. Data-hungry deep learning methods started to dominate accuracy benchmarks around 2012. The Kinect, which provides a 30-body motion interface for the Xbox 360 and the Xbox One, uses algorithms that emerge from lengthy AI research, as do intelligent personal assistants in smartphones. In March 2016, AlphaGo won 4 out of 5 games of Go in a match with Go champion Lee Sedol, becoming the first computer Go playing system to beat a professional Go player without any handicaps. In the 2017 Future of Go Summit, AlphaGo was a 3-game match with Kiji, who at the time continuously held the world number 1 ranking for 2 years. This marked the completion of a significant milestone in the development of artificial intelligence, as Go is a relatively complex game, more so than chess. According to Bloomberg's Jack Clark, 2015 was a landmark year for AI, with the number of software projects that use AI within Google increased from a sporadic usage in 2012 to more than 2,700 projects. Clark also presents factual data indicating the improvements of AI since 2012, supported by lower error rates in image processing tasks. He attributes this to an increase in affordable neural networks due to the rise in cloud computing infrastructure and to an increase in research tools and datasets. Other cited examples include Microsoft's development of a Skype system that can automatically translate from one language to another, and Facebook's system that can describe images to blind people. In a 2017 survey, 1 in 5 companies reported that incorporated AI in some offerings or processes. Around 2016, China greatly accelerated its government funding given its large supply of data and its rapidly increasing research output. Some observers believe it may be on track to becoming an AI superpower. However, it has been acknowledged that reports regarding AI have tended to be exaggerated. A typical AI analyzes its environment and takes actions that maximize its chances of success. An AI's intended utility function or goal can be simple or complex. Goals can be explicitly defined or induced. If the AI is programmed for reinforcement learning, goals can be implicitly induced by rewarding some types of behavior or punishing others. Alternatively, an evolutionary system can induce goals by using a fitness function to mutate and preferentially replicate high-scoring AI systems, similar to how animals evolved to innately desire certain goals, such as finding food. Some AI systems, such as nearest neighbor, instead of reason by analogy, these systems are not generally given goals except to the degree that goals are implicit in their training data. Such systems can still be benchmarked if the non-goal system is framed as a system whose goal is to successfully accomplish its narrow classification task. AI often revolves around the use of algorithms. An algorithm is a set of unambiguous instructions that a mechanical computer can execute. A complex algorithm is often built on top of another simpler algorithms. Many AI algorithms are capable of learning from data. They can enhance themselves by learning new heuristics, strategies, or rules of thumb that have worked well in the past, or can themselves write other algorithms. Some of the learners described below, including Bayesian networks, decision trees, and nearest neighbor, could theoretically learn to approximate any function, including which combination of mathematical functions would best describe the work. These learners could therefore derive all possible knowledge by considering every possible hypothesis and matching them against the data. In practice, it is seldom possible to consider every possibility because of the phenomenon of combinatorial explosion, where the time needed to solve the problem grows exponentially. Much of AI research involves figuring out how to entirely identify and avoid considering a broad range of possibilities unlikely to be beneficial. The earliest approach to AI was symbolism, such as formal logic. If an otherwise healthy diet has a fever, then they may have an influence. A second, more general approach is Bayesian influence. After examining the records of known past patients whose temperature, symptoms, age, and other factors mostly match the current patient, X% of those patients turned out to have influenza in such and such a way. The third major approach, extremely popular in routine business AI applications, are analogies. Fourth approach is harder to intuitively understand but is inspired by how the brain's machinery works. The artificial neural network approach uses artificial neurons that can learn by comparing itself to the desired output and altering the strength of the connections between its internal neurons to reinforce connections that seem to be useful. These four main approaches can overlap with each other and with the evolutionary system. Some systems implicitly or explicitly use multiple of these approaches alongside many other AI and non-AI algorithms. The best approach is often different depending on the problem. Learning algorithms work on the basis that strategies, algorithms, and inferences that work well in the past are likely to continue working well in the future. These inferences can be obvious, such as since the sun rose every morning for the last 10,000 days, it will probably rise tomorrow morning as well. This can be new ones, such as the X% of families are geographically species with color variants, so there is a 1% chance that undiscovered black swans exist. Learners also work on the basis of Occam's razor, the simplest theory that explains the data is the likeliest. Therefore, according to Occam's razor principle, a learner must be designed such that it prefers simpler theories to complex theories, except in cases where the complex theory is proven substantially better. Settling, settling on a bad, overly complex theory gerrymandered to fit all the past training data is known as overfitting. Many systems attempt to reduce overfitting by rewarding a theory in accordance with how well it fits the data, but penalizing the theory in accordance with how complex the theory is. Besides classic overfitting, learners can also disappoint by learning the wrong lesson. A toy example is that an image classifier trained only on pictures of brown horses and black cats might conclude that all brown patches are likely to be horses. Compared with humans, existing AI lacks several features of human common sense reasoning. Notably, humans have powerful mechanisms for reasoning about naive physics, such as space, time, and physical interactions. This enables even young children to easily make inferences. If I roll this pen off a table, it will fall on the floor. Gravity. Humans also have a powerful mechanism of folk psychology that helps them to interpret natural language sentences such as a city councilman refused to the demonstrators a permit because they advocated violence. This lack of common knowledge means that AI often makes different mistakes that humans make in ways that can make seem incomprehensible. For example, existing self-driving cars cannot reason about the location or the intentions of pedestrians in the exact way that humans do, and instead must use non-human modes of reasoning to avoid accidents. The cognitive capabilities of current architectures are very limited, using only a simplified version of what intelligence is really capable of. For instance, the human mind has come up with ways to reason beyond measure and logical explanations to different occurrences in life. What would have been otherwise straightforward and equivalently difficult problem may be challenging to solve computationally as opposed to using the human mind. This gives rise to two classes of models, structuralist and functionalist. The structural models aim to loosely mimic the basic intelligence operations of the mind, such as reasoning and logic. The functional model refers the correlating data to its computer counterpart. The overall research goal of AI is to create technology that allows computers and machines to function in an intelligent manner. Otherwise, there is no point in calling it as AI. The general problem of simulating or creating intelligence has been broken down into subproblems. These consist of particular traits or capabilities that researchers expect an intelligent system to display. The traits described below have received the most attention. Early researchers developed algorithms that imitated step-by-step reasoning that humans use when they solve puzzles or make logical deductions. By the late 1980s and 1990s, AI researchers developed methods for dealing with uncertain or incomplete information, employing concepts from probability and economics. These algorithms proved to be insufficient for solving large reasoning problems because they experienced a combinatorial explosion. They became exponentially slower as the problems grew larger. Even humans rarely use the step-by-step deduction that early AI research could model. They solve most of the problems using fast, intuitive judgments. Knowledge representation and knowledge engineering are central to classical AI research. Some expert systems attempt to gather explicit knowledge possessed by experts in some narrow domain. In addition, some projects attempt to gather the common sense language known to the average person into a database containing extensive knowledge about the world. Among the things a comprehensive common sense knowledge base would contain are objects, properties, categories, and relations between objects, situations, events, states, and time, causes and effects, knowledge about knowledge, and many other less well-researched domains. A representation of what exists is ontology, a set of objects, relations, concepts, and properties formally described so that software agents can interpret them. The semantics of these are captured as description logic concepts, roles, and individuals, and typically implemented as classes, properties, and individuals in the web ontology language. The most general ontologies are called upper ontologies. which attempt to provide a foundation for all other knowledge by acting as mediators between domain ontologies that cover specific knowledge about a particular knowledge domain. Such formal knowledge representations can be used in content-based indexing and retrieval, scene interpretation, clinical decision support, knowledge discovery, and other areas. Among the most difficult problems in knowledge representation are default reasoning and the qualification problem. Intelligent agents must be able to set goals and achieve them. They need a way to visualize the future, a representation of the state of the world, and be able to make predictions about how their actions will change and be able to make choices that maximize the utility of available choices. In classical planning problems, the agent can assume that it is the only system acting in the world, allowing the agent to be certain of the consequences of its actions. However, if the agent is not the only actor, then it requires that the agent can reason under uncertainty. This calls for an agent that cannot only assess its environment and make predictions, but also evaluate its predictions and adapt based on its assessment. Multi-agent planning uses the cooperation and competition of many agents to achieve a given goal. Emergent behavior such as this is used by evolutionary algorithms and swarm intelligence. Machine learning (ML), a fundamental concept of AI research since the field's inception, is the study of computer algorithms that improve automatically through experience. Unsupervised learning is the ability to find patterns in a stream of input without requiring a human to label the inputs first. Supervised learning includes both classification and numerical regression, which requires a human to label the input data first. Classification is used to determine what category something belongs to and occurs after a program sees a number of examples of things from several categories. Regression is the attempt to produce a function that describes the relationship between inputs and outputs and predicts how the outputs should change as the inputs change. Both classifiers and regression learners can be viewed as function approximators trying to learn an unknown, possibly implicit function. For example, a spam classifier can be viewed as learning a function that maps from the text of an email to one of the two categories, spam or not spam. Computational learning theory can assess learners by computational complexity, by sample complexity, or by other notions of optimization. In reinforcement learning, the agent is rewarded for good responses and punished for bad ones. The agent uses this sequence of rewards and punishments to form a strategy for operating in its problem space. Natural language processing (NLP) allows machines to read and understand human language. A sufficiently powerful natural language processing system would enable natural language user interfaces and the acquisition of knowledge directly from human written sources, such as news via text. Some straightforward applications of NLP include information retrieval, data text mining, question answering, and machine translation. Many current approaches use word co-occurrence frequencies to construct syntactic representations of text. Keyword spotting strategies for research are popular and scalable but dumb. The search query for dog might only match documents with a literal word dog and misses a document with the word poodle. Lexical affinity strategies use the concurrence of words such as accident to assess the sentiment of a document. Modern statistical NLP approaches can combine all these strategies as well as others and often achieve acceptable accuracy at the page or paragraph level. Beyond semantic NLP, ultimate goal of narrative NLP is to embody a full understanding of common sense reasoning. By 2019, transformer-based deep learning architectures could generate coherent text. Machine perception is the ability to use input from text sensors such as cameras, microphones, wireless signals, and active lidar, sonar, radar, and tactile sensors to deduce aspects of the world. Applications include speech recognition, facial recognition, and object recognition. Computer vision is the ability to analyze visual input. Such input is usually ambiguous. A giant 50-meter tall pedestrian far away may produce the same pixels as a nearby normal-sized pedestrian, requiring the AI to judge the relative likelihood and reasonableness of different interpretations. For example, by using its object model to assess that 50-meter pedestrians do not exist. AI is heavily used in robotics. Advanced robotic arms and other industrial robots widely used in modern factories can learn from experience how to move efficiently despite the presence of friction and gear slippage. A modern mobile robot, when given a small static and visible environment, can easily determine its location and map its environment. However, dynamic environments such as in endoscopy, the interior of a patient's breathing body pose a greater challenge. Motion planning is a process of breaking down movement tasks into primitives such as individual joint movements. Such movement often involves compliant motion, a process where movement requires maintaining physical contact with an object. Moravac's paradox generalizes the low-level sensorimeter skills that humans take for granted are counterintuitively difficult to program into a robot. The paradox is named after Hans Moravac, who stated in 1988 that if it is comparatively easy to make computers exhibit adult-level performance in intelligence tests are playing checkers and find difficult or impossible to give them the skills of a one-year-old when it comes to perception and mobility. This is attributed to the fact that unlike checkers, physical dexterity has been a direct target of natural selection for millions of years. An intelligent agent is a system that perceives its environment and takes actions that maximize its chances of success. The simplest intelligent agents are programs that solve specific problems. More complicated agents include human beings and organizations of human beings. AI is relevant to any intellectual task. Modern AI techniques are pervasive and are too numerous to list here. Frequently, when a technique reaches a mainstream use, it is no longer considered AI. This phenomenon is described as the AI effect. High-profile examples of AI include autonomous vehicles, medical diagnostics, creating art, proving mathematical theorems, playing games, search engines, online assistants such as Siri, image recognition in photographs, spam filtering, predicting flight delays, prediction of judicial decisions, targeting online advertisements, and energy storage. With social media sites overtaking TV as a source for news for young people, and news organizations increasingly reliant on social media platforms for generating distribution, major publishers now use AI technology to post stories more effectively and generate greater volumes of traffic. AI can also produce deepfakes, yes, content altering technology. There are three philosophical questions related to AI. Whether artificial general intelligence is possible, whether a machine can solve any problem that a human being can solve using intelligence, or if there are hard limits to what a machine can accomplish. Whether intelligent machines are dangerous, certainly they are dangerous. How humans can ensure that machines behave ethically and that they are used ethically. Whether a machine can have a mind, consciousness, and mental states in the same sense that human beings do. If a machine can be sentient and thus deceive certain rights, and if a machine can intentionally cause harm. Emotion. Human beings have emotion, humans, animals. Machines with intelligence have the potential to use the intelligence to prevent harm and minimize risks. They may have the ability to use ethical reasoning to better choose their actions in the world. As such, there is a need for policy making to devise policies for and regulate AI and robotics. The field of machine ethics is considered with giving machines ethical principles or procedures for discovering a way to resolve the ethical dilemmas they might encounter, enabling them to function in an ethically responsible manner through their own ethical decision making. If an AI system replicates all key aspects of human intelligence, all that will the system also be sentient? Will it have a mind which has conscious experiences? The question is closely related to the philosophical problem as to the nature of human consciousness, generally referred to as the hard problem of consciousness. Superintelligence, hyperintelligence, or superhuman intelligence is a hypothetical agent that would possess intelligence far surpassing that of the brightest and most gifted human mind. Superintelligence may also refer to the form of degree of intelligence possessed by such an agent. Widespread use of AI could have unintended consequences that are dangerous or undesirable. Some are concerned about algorithmic bias, that AI programs may unintentionally become biased after processing data that exhibits bias. The development of full artificial intelligence will spell the end of human race. Once humans develop AI, it will take off on its own and redesign itself at an ever increasing rate. Humans who are limited by slow biological evolution could not compete and would be superseded. This is by Stephen Hawking. The regulation of AI is the development of public sector policies and laws for promoting and regulating AI. AI-based technology has achieved many great things such as facial recognition, medical diagnostics, and self-driving cars. AI promises enormous benefits for economic growth, social development, as well as human well-being and safety improvement. However, the low level of explainability, but data biases, data security, data privacy, and ethical problems of AI-based technology pose significant risks for users, developers, humanity, and societies. As AI advances, one critical issue is how to address ethical and moral challenges associated with AI. Even though the concept of machine ethics was proposed around 2006, AI ethics is still in its infancy. AI ethics is a field related to the study of ethical issues in AI. To address AI ethics, one needs to consider the ethics of AI and how to build ethical AI. Ethics of AI studies that the ethical principles, rules, guidelines, policies, and regulations that are related to AI. Ethical AI is an AI that performs and behaves ethically. One must recognize and understand the potential ethical and moral issues that may be caused by AI to formulate the necessary ethical principles, rules, guidelines, policies, and regulations for AI. With the appropriate ethics of AI, one can then build AI that exhibits ethical behavior. Ethics can be defined as a moral principles governing the behaviors or actions of an individual or a group of individuals. In other words, ethics are a system of principles or rules of guidelines that help determine what is good or right. Broadly speaking, ethics can be defined as a discipline dealing with the right versus wrong, the moral obligations and duties of entities. Some people have a myth that with machines one can rule this world. AI is just a tool and it should be used judiciously, and humans should always retain the upper hand. Else, it may lead to mass extinction of human race from this planet. Machines should be our slaves and not the vice versa. Never work against nature. Lead a harmonious life with the nature created by the superpower. Nowadays, humans are acting against nature like ruining environment, deforestation, water sources, exploitation of natural resources, etc. As a result, we are paying a high price like proliferation of pandemics, El Nino, tornadoes, hurricanes, tsunamis, volcano eruptions, flooding, proliferation of industrial accidents. We need to put a stop to all these once and for all for our own good. Else our days are counted. Debates, discussion on topics like this, open-ended topics like this can go on forever. Anyhow, let me pull the plug here. We'll meet again real soon with another interesting topic. Some of the statements, views expressed are solely mine, based on limited knowledge gained over 6 decades of versatile experience. Always watch these videos with a closed caption for absolute 100% comprehension as per my sincere recommendation zillion times so far. I know I rushed through to complete the presentation within 20 minutes max, which is a norm I had set myself to retain the viewer's attention. I know nowadays I take almost double the time since I make honest attempts to cover the selected topic more elaborately, including so many fine details, intricate details, referring a wide variety of sources, in particular Wikipedia quite extensively, besides articles and books published recently. Besides, of course, I sprinkle my own salt and pepper and season it with my personal experiences so far in my life and also intuition. Stay at home as much as possible to maintain social distance. Social distancing attributed to pandemic novel COVID-19 and prolong your lifespan. Lead a healthy life. Government can put a stop to natural and unnatural events, maybe via wars and cyber war. Events like pandemics, which may lead to apocalypse and extinction of all sentient species on Earth for no fault of theirs. Rest in peace and harmony.